deduce that the principle of equivalence predicts that time slows down near a massive body. Let's look at this spaceship. We have a spaceship which is just taking off, and we have two clocks, one at the top and one at the bottom. What will happen is that the clock at the top of the spaceship, if this accelerates, will go faster than the clock near the bottom of the spaceship. So clock A will go faster than clock B. Why is that? You'll have to accept it. I will go through an argument here, but you don't really need to be able to recount the argument. Let's take that the rocket takes off on the bottom and accelerates as it goes up here. So the ship is accelerating upwards. We have an observer at the bottom of the ship. Looks at the light signal from the top of the ship, which is at point A. Clock A emits this signal, this pulse of light, which is received at B. But in that time, because it's moving, B is moved to this point here. So it moves to meet it. So this pulse goes a distance L1, which is basically from where it leaves A to where B reaches it at this point here. So from our point of view, it goes this distance L1. The next pulse, the ship has already accelerated considerably, and the next one goes from A to B, but the ship is going faster now because it has accelerated. And now we compare this length to this one. Well, the ship is going faster, so when the pulse leaves A and is picked up by B, that length will now be shorter. So length 2 is shorter than length 1, because everybody must agree on the speed of light, and since it's going faster, that distance that the light travels is going to be shorter. Now we know that time is equal to distance divided by speed. We know that the distance is shorter, the speed is going to be the same, so the time will be less. So basically what happens is that B observes the ticks which are closer together. The time from one tick to another is going to be quite short. Because the distance is shorter, the time between ticks is going to be shorter, which means that when B observes the clock in A, it's going to be ticking quickly. So the clock in A will be moving faster than the clock in B, from B's perspective. If a signal was sent from B to A, it has a certain distance to travel there. By the time it goes from B to A here, the distance is further. A longer distance with the same speed means that time will be going slower. So when A looks at the clock on B, long time between each tick. So when A looks at B's clock, their clock goes slower. The clock at the top goes quickly, the clock at the bottom goes slowly. Another shorter explanation can be this. Since the speed of light is independent of the source, as B observes A, the distance appears to be getting shorter. So it means that the wavelengths, the light that is leaving, will be blue shifted. The distance will be getting shorter, the wavelength will be getting shorter, so it becomes blue shifted. That means a higher frequency. As A observes B, the distance between them will be getting longer. In other words, the wavelength of light going from B to A will get longer, so it becomes redshifted. And this is because of the acceleration. We have an accelerating frame of reference. Now remember this, the clock at the top is moving quickly, the clock at the bottom is moving slowly. Remember, this is an accelerating frame of reference. The principle of equivalence says that gravity must also do the same thing, because there's no way of distinguishing between an accelerating frame of reference and a gravitational frame of reference. Means that this will be the case, that in a gravitational field, the clock at the top will be going faster than the clock at the bottom. So gravity affects the rate at which clocks run. High clocks run faster, low clocks run slow. The twin paradox. The body that ages the least is the one that accelerates. The accelerating frame of reference is the same as one that's been in a strong gravitational field, so their clocks will go slower. So the moving twin, the one that goes to the distant galaxy and accelerates back again, is going to age slower. This has been proven by observations from quasars. These are quasi-stellar objects, stellar-like objects, which we know are near large gravitational objects. Their light has been shifted so far that they've gone into the red and infrared part of the spectrum. And this is due to gravitational redshift. So the prediction of the general theory of relativity, in which clocks slow down in a gravitational field, in other words, clocks on the ground floor of a building will run slower than the clocks compared with the top floor. Or in other words, light from the top floor observed from the ground is going to be blue shifted. Light from the ground floor observed from the top is red shifted. This graphic shows this. High clocks run fast, slow clocks are low. Low, slow. Also, when radiation leaves the bottom of the building goes up, it will be slightly redshifted. You might say that, oh, but the energy of the photon is what it is, and the frequency must be the same. But as the light leaves or moves up in a gravitational field, it must be losing some energy. It loses some energy because it's gaining height in the gravitational field. So what's going to happen is that the energy will get less, the frequency will get less. Light from the bottom will be redshifted by the time it gets to the top. But light from the top will gain energy, will become blue shifted as it moves down. And here we have it here. A robot probe near a black hole, a large, massive gravitational object, sends visible light. By the time you observe that at 10,000 kilometers, it will be in the radio part of the spectrum. If it emits in the X-ray part of the spectrum, by the time it gets here, it will become so redshifted, it will be in the visible part of the spectrum. You have to solve problems. Here's a question, past paper question, that was answered very badly. Here we have a spaceship which is going at a constant speed, but then it starts to accelerate. You have to explain why to Elspeth the light from the source close to Alex will be observed to be of a lower frequency. It will be red shifted. So you first of all have to state that since both will observe the speed of light as being the same value, as it accelerates, the distance between them, from Elspeth's point of view, the distance between them, the distance to Alex, will get longer and longer and longer, which means the wavelength will become more and more redshifted. Also, from Alex's point of view, since they're accelerating to the right, the distance to Elspeth will get shorter and shorter and shorter, so any light from her will be blue shifted, but this is not what the question is asking. Since the speed of light is independent of the speed of the source, Alex's source will appear to be moving away from Elspeth as the acceleration increases. So according to the Doppler effect, the light will have to appear redshifted. The examiner's reports that this question was very badly answered. The students could recall some facts but could not structure it to form a coherent argument. You need to be able to apply this equation to find out what is the degree of gravitational redshift, what is the change in the frequency with the original frequency in small changes of height. It has to be small changes of height because we have g as being a constant value. For example, a signal is sent from the base of a building. What is the change in the frequency from the top to the bottom? What does the top observe? Well, they're going to observe a slightly different frequency. Will it be higher or lower? And what frequency do they tune to? You could try to do that now. Is this. They basically tune to a slightly lower frequency, but it's so similar to the other frequency, the tuning device will still pick up the same frequency.